All right, so good morning. Hope everyone had a nice weekend. We are getting started on chapter 7. Which is all on chemical equations and balancing chemical equations. So, we sort of start in chemistry just like you'd start with writing. You start with the alphabet. So we started with the elements, and then we put the letters together and made words, or we put the elements together and made compounds. And now we're going to take the compounds and we're going to string them together into sort of a sentence, which will be our chemical reaction, which is where we take two different compounds or 3 or 100 different compounds, and we kind of mix them together so that the atoms move around and change places. So as far as evidence of a chemical reaction, if you ever made one of these volcanoes for a science project when you were a little kid, use vinegar and baking soda. This is a neutralization reaction. One of the products that's formed is carbon dioxide. The carbon dioxide will bubble out of solution, and that's what causes it to erupt. This is specifically called a gas evolution reaction. We'll look at that a little later. You can add red food coloring to it, but that doesn't really have any chemical effect. As far as a chemical reaction that's happening every time you drive your car, it's called a combustion reaction. And that's where you take octane, which is a component in gasoline. You mix it with oxygen. Well, you don't mix it, but you react it with oxygen. Mixing it, they would just sort of sit together, but they're actually reacting. So the octane reacts with oxygen, it moves through your engine. Your engine captures the heat that's produced to move pistons that will run the car. And then your products are carbon dioxide and water. Combustion reactions, this type of reaction is a subcategory of an oxidation reduction reaction, and we'll get into that a little bit later. Chemical laundry detergent, we don't need to get into that one. Okay, so as far as evidence of a chemical reaction, if you could actually see the atoms and the molecules that compose compounds, you would know that a chemical reaction occurred because atoms would combine with other atoms to form compounds, or new molecules would form, or original molecules will decompose. Atoms in one molecules would change with atoms of another. So what you would be seeing is that all the atoms would be sort of swapping partners, changing out. If we could see the atoms and molecules composed of matter, we could actually see that a chemical reaction has in fact occurred, but we can't see with our eye atoms, individual atoms and molecules, so we have to look at secondary things to tell us that a chemical reaction has occurred. Some things that indicate that a chemical reaction has occurred, a color change. That isn't always the case with color change. Sometimes we can have a color change and it isn't a chemical change, it's a phase change. We can have the formation of a solid. That is definitely a good indicator of a chemical reaction. Hold on 1 second. It's driving me nuts. There we go. So if we have like 2 liquids that come together and all of a sudden a solid forms out of them, that's letting you know that a new material has formed. If we have the production of gas when you add something to a solution, that could be a good indicator. And I don't mean like you're boiling a pot of water and like it's vaporizing and gas is forming. I'm talking about 2 things that are at room temperature. You're not applying heat like that. You mix them together and all of a sudden gas forms. The emission of light, so like these glow sticks over here, that's a chemical reaction. And also anytime you produce heat or you absorb heat. So if the material gets really hot or if the materials that you're combining together get really, really cold, that can be an indicator of chemical reaction. So here's a precipitate. We've got this yellow material that probably has iron in it. And then this clear liquid, when you drop it in, all of a sudden this solid starts to form or precipitate out. That would be a good indicator of chemical reaction. Over here on the right, this is a gas evolution. You have a little Alka-Seltzer dropped into water, and we start to get this effervescent quality or fizzing. This is not a chemical reaction, okay? It kind of looks like the last one, right? Like this is kind of fizzy, and this looks like it's bubbly fizzy, but why is this not a chemical reaction? Well, what's happening here when you're boiling a pot of water? Are you creating something new or breaking something down? No, it's staying the same thing. In the liquid form, it is H2O molecules. In the gaseous form, it is also simply H2O molecules. They're just changing phases. So instead of the molecules being packed really close together, they've got enough kinetic energy that they can spread out. So we've now formed a gas version of the H2O. As far as if we were to want to fully prove that a chemical reaction has occurred, only a chemical analysis that shows what the initial substances are and the final substances could actually prove that a chemical reaction has occurred. There are sometimes that chemical reactions can occur without any obvious signs. So it doesn't change color, it doesn't produce heat, it doesn't do any of those things, but there is in fact a chemical change that's occurring. And the changes that occur at an atomic and molecular level determine whether a chemical reaction has taken place, even if you can't see it on a macroscopic. So know that there are reactions out there that can happen that it doesn't look like anything's going on. You've got a clear liquid and a clear liquid and you pour them together and the thing that you get is a clear liquid and doesn't look like much has happened, but things have definitely changed. So if we're talking about a chemical reaction, we need to be able to explain that to somebody in a relatively simple way. So we have these things called chemical equations. So a chemical equation has, you read it like you would read a book from left to right. So on the left side of your chemical reaction, you have your reactants or what you're starting with. Then you'll have an arrow. And then on the right side, you'll have your products. The arrow, why I'm so yawny this morning. The arrow represents the chemical change. So it'll look something like this. We've got reactants, arrow, and then products. How many reactants do you have? You have to have at least one, but you could have many, many more than one. How many products do you have? You have to have, again, at least one. Otherwise, a reaction hasn't occurred. The arrow is where the reaction is taking place. A lot of times, you're just going to get a yawning teacher today. It is not that I'm disinterested. I don't know why it's happened. A lot of times, the reactants and products will be given with the phase. So is it being presented as a solid, a liquid, or a gas? So you may see that as a little symbol with parentheses coming after it. So gas will get a little G, liquid will get a little L, solid will get S, and then we have this other one called AQ. AQ means aqueous, means that you're bringing the material as a water solution. So many chemical reactions on Earth happen in water states that it gets its own little phase. So, it's important to note, is the sodium chloride, which is salt, being brought to the situation as a solid, or is it being brought to the situation or the reaction as aqueous? Okay, if you see it like this, that means it's solid salt form, like that you probably have on your table. If it's like this, it means that it's salt dissolved in water. So here's a chemical equation for the combustion of methane. And if you're looking at the word methane and thinking, I can't come up with a chemical equation or a chemical reaction, or a chemical formula for that, that's because that's an organic. So I wouldn't expect you to know that methane is CH4, right? But you do need to know that sodium chloride is NaCl. You would need to know that silver nitrate is AgNO3. You need to still know your nomenclature. But for this one, we've got a reaction occurs with methane. It reacts with oxygen and it forms CO2 and water. So if you're ever given something that's like a word problem like this, where it has this, here are words, it doesn't give you these things, you would need to write the correct formulas for each thing. The to form is your arrow, and then these are your products, right? So we've got 2 reactants and 2 products. If we add the states to this, these are gases. Actually, all of them are gases. So 2 gases come together and your products will be gases as well. So this would be an example of a chemical equation for the combustion of methane. Methane combines with oxygen to produce CO2 and H2O. And you also get energy or heat. They don't have it written there, but I mean, that's the whole point of combusting methane, right? That's why we combust hydrocarbons, so that we can produce energy to run all of our stuff. Whew. So one thing that's going on with this equation, though, is it's not balanced. What does the law of conservation of mass tell us? The law of conservation of mass says that in a chemical reaction, matter isn't created or destroyed. So the number of atoms that you're starting with needs to be equal to the number of atoms that you're ending with. So if looking at this equation here, I have 2 oxygens that I start with, right? O2. When I end, though, I have 1, 2, 3 oxygens, right? 2 coming from the CO2 and 1 coming from the water, for a total of 3 oxygen atoms. So we started with 2 oxygen atoms, we ended with 3 oxygen atoms. In a chemical reaction, that is not possible. You can't just like pull an oxygen atom out of thin air. What you're starting with atom-wise has to equal what you're ending with. So we need to adjust this equation so that the number of atoms that we're starting with is equal to the number of atoms that we're ending with. You need to be accountable for all the atoms. There's another issue here. If we look, methane has 4 hydrogens. Water over here only has 2 hydrogens. So like 2 of the hydrogens just disappeared. No, that's not what's happened. What's going on is that this equation isn't balanced, or the proportions aren't correct. So we need to balance this equation. And the way we balance equations is we put coefficients in the front, or numbers. You can think of them as numbers, multipliers, or coefficients in the front, so that we can balance it out. We never change subscripts. Like I would never want to do this. This is bad. So what did we say? We had 3 oxygens over here and we only have 2 oxygens over here, right? I would never want to just go, oh, well, I'm going to change this to a 3. Why? Because oxygen isn't a triatomic molecule, it's a diatomic molecule. So the first thing you always have to do is honor what the correct formula is. Another thing I wouldn't do, if there's 4 hydrogens here and there's 2 hydrogens here, I can't just change this to H4O. Is H4O water? No, that's no longer water. So we never change subscripts. We always change coefficients, or these things that sit in the front. Right now, you don't see it, but there's an assumed 1 coefficient in each of these places. If you've written it, it means you have one of them, right? I wouldn't write methane and then tell you, oh, wait, just kidding, there's no methanes. So there's an inferred 1 there, and we can change that 1 to 2 or 3 or 4 or whatever. So here is an example of a balanced version. If instead of having a 1 to 1 to 1 to 1 ratio, I put a 2 here and a 2 here. So I double the amount of oxygens, or diatomics, and I double the waters. Well, what happens now is, let's see, we've got carbon, we've got hydrogens, and we've got oxygens. On this side, I have 1 carbon. On this side, I have 4 hydrogens. And now how many oxygens do I have? I have 4 oxygens, right? What about on this side? How many carbons? I still only have 1 of those black carbons. How many oxygens do I have? The red ones, 1, 2, 3, 4. I have 4 hydrogens. I'm sorry, 4 oxygens. And then hydrogens, which are the white ones, 1, 2, 3, 4. I also have 4. So do you see now how there's the same number on both sides? So we haven't, created or destroyed anything. What we're saying now is that the equation isn't actually one of these and one of these produces one of these and one of these. What we're saying is 1 methane will combine with 2 oxygens, and your resulting products will be 1 CO2 molecule and 2 water molecules. Okay. And if you're wondering, well, how do you get a 2 and a 2? Like how did, of all the numbers you could have picked, why is it 2 on those? I will show you guys how to balance that, okay? There is a system to it. But is that making sense, what's going on here with the number of atoms on both sides needing to be the same? Okay, great. So let's balance something. Come on, give me something. Okay, so how to balance a chemical equation. The first thing you need to do is write what they call a skeletal equation for the correct chemical formula. This has a lot to do with nomenclature. A lot of times this is already given to you. Step 1 is given to you. It's given you equation and it's just not balanced. If it doesn't give that to you, if it gives it to you as a word problem, you've got to come back around with nomenclature, and we'll do a little practice of that. So once you've got your skeletal formula, like for instance, this would be an example of a skeletal formula. It just has the relative compounds in their respective places, right? So it tells you the reactants, it tells you the products, they're separated by pluses. It's not balanced though. Now we've got a balance. So as far as rules go, if an element occurs in only one compound on both sides of the equation, balance it first. So like looking back here, do you see how carbon is only in one compound on both sides? And hydrogen is also only in one compound on both sides. We would want to balance those first. Do you see how oxygen is in 2 compounds over here? It's like it's only in one compound here and then it splits up. Leave that for the end. Balance that at the end. Hope that when you balance the other things, that gets cleared up, okay? So balance those first. If there's more than one of those elements, balance metals before non-metals. I don't know, it just sort of works out better if we do the metals before the non-metals. It's not super strict on that, but if it is split up, leave it to the end. This one's a good one. If an element occurs as a free element on either side, meaning it's by itself or it's a diatomic by itself, balance that last. Because like if we're looking at this, I'm going to balance this thing last, because if I put a coefficient, it doesn't affect anything else, right? If I put a coefficient here, it affects not only the oxygen, it also affects the hydrogen. So if I leave this at the very, very end, I can kind of just balance that, and I know it's not going to mess with any of my other things. If the balanced equation for whatever contains a coefficient fraction, change those into whole numbers by multiplying everything by an appropriate factor. So I'm just going to give you like a random hypothetical. So let's say we had CH3, that's not even a thing really, but plus O2 gives us CO2 and H2O. Let's say that for whatever reason, this had a 1.5 as a coefficient. I'd want to get rid of that and multiply everything by 2. So this would become a 3, CH3. This would become a 2. This would become a 2. And this would become a 2, H2O. That's probably not even correctly balanced, but just for the sake of it, if one of these happens to be like a half, multiply everything by 2, it'll affect all of them. You probably won't see that very often, but if you do bump into it, that's a good thing to know. Check to make sure the equation is balanced by summing the total numbers of each atom on both sides. I kind of do this first. I'll show you my system. This one, this check 5, or this 5, I kind of do it as I go along. And then remember, change only coefficients. Never change subscripts. Because if you change the subscripts, what are you changing? What you're talking about, right? If I said sodium chloride, it better look like that. It better not look like this, because you want to have 2 sodiums. If you want to have 2 sodiums, you got to put it in front. You don't change the subscript. So let's look at this guy right here. We've got aluminum combines with sulfuric acid to produce aluminum sulfate and hydrogen gas. I'm going to write this on my, it's the lovely work of my daughter. This program, it will like snap shapes if you get it just right. Like if you make a square, it'll snap it into a square. And my daughter just finds that so intriguing. So she's always on my computer trying to get the shapes to snap. And then she'll run and be like, Mommy, I snapped the shape and I'm like, oh my gosh, you erased all the nomenclature. You have to write all that stuff down again. Okay, so, and she picks all the rainbow colors. Where's my purple? All right, aluminum. And it gave us the phases. So it said it was solid aluminum, H2SO4. I'm assuming that this is aqueous. It's usually how we produced. And then we've got Al, 2SO4, 3, aqueous, plus hydrogen gas. Yeah, okay, so make sure I have the right phases. So when I'm balancing these, I like to take inventory first. So what is present? I've got aluminum, I've got hydrogen, and then do you guys notice how the sulfate ion stays sulfate? Like it's sulfate over here and it's sulfate over here. If that happens, you can just take that as a packet. You don't have to break the sulfurs and the oxygens apart. Now, if that sulfate ion happened to turn into sulfur in one thing and oxygen in another thing, and it no longer was neat and compact, take the sulfur and the oxygen separately. But since it's a packet, I'm going to just take them as a whole. So I like to write out on each side of what I have how many there are. So starting, I have 1 aluminum. So I'm going to put a little 1 on the left-hand side. Hydrogens, I have 2. So I'm going to put a 2 there. Sulfates, as a packet, I am starting with just 1 sulfate, right? Now, what is on the product side currently? There are 2 aluminums, so I'm going to put a 2 on this side. How many sulfate, hydrogens rather? There's 2 hydrogens. And how many sulfates? This is saying I have 3 sulfates. So right now the hydrogens are balanced, the aluminums aren't, and the sulfates aren't. Now, I mean, I guess I could balance the aluminums first. It's kind of by itself though, so I'm going to mess with the sulfates first. There's 3 sulfates on this side, so I need to get 3 sulfates on this side. I cannot put parentheses here and put a 3 around the outside. I can't mess with the subscripts. The only thing I can do is change the coefficient. So I'm going to put a 3 in front of this thing. Now that 3 gets distributed to everything. So how many sulfates do I have? I now have 3, but what happens to my hydrogens? That turns it to 6. 3 times the 2 gives me 6. And if you're thinking, well, the hydrogens were balanced and now they're not balanced, that does happen. Sometimes you have to unbalance one thing to balance the other, and then you go back around and fix it. So the 3 is taking care of my sulfate. Now I can go ahead and balance my hydrogens or my aluminums. Let's balance the hydrogen since we're already around there. So there's 6 on this side. So how many do I need on that side? I also need 6. I'm going to make a little bit more space here. So if I want 6 hydrogens, what can I put in front of this hydrogen here? I'm going to put a 3. All right, that will change this to 6. What's the last thing that needs to get balanced? The aluminum. There's 2 aluminums on the product side. I need 2 aluminums on the starting side. That's a really easy fix, right? We just throw a 2 in front of there, and now we are balanced. So the equation isn't a 1-to-1 ratio. It's saying 2 aluminums have to combine with 3 sulfuric acid molecules to produce 1 aluminum sulfate molecule and 3 hydrogen gas molecules. Now we're all balanced. The system says to go ahead and check. Well, if you're doing it this way, where you're kind of crossing them out as you go, you've checked as you've gone along. You can always double check if you want to, but that should work out. So each of these numbers on the lines need to equal each other. 2, 2, 6, 6, 3, 3. Great. Okay. So, and then the slides are done. They're like, you know how to balance, you're good. So we're going to do a little bit more practice with that. Let's do, I've got a sheet here. Where did you go? Okay, let's do a couple of these. So N2 plus H2 gives us NH3. N2 plus H2 gives us NH3. So pretty simple equation. Nitrogen gas plus hydrogen gas come together to form ammonia. So we've got nitrogens and we've got hydrogens. Why do these have little 2's on them? You know, why isn't it just nitrogen by itself? What do the 2's indicate? Remember diatomics. Those will come into play because if for some reason I wrote it as a word problem and I said, hey, nitrogen combines with hydrogen. Okay, and you just write it as this. That is not going to be correct. You got to make sure you're putting 2's in wherever you have diatomics. So that's why that has a 2 there. All right, so we've got 2 nitrogens and 2 hydrogens. I'm ending with 1 nitrogen and 3 hydrogens. Those are definitely not balanced. So we need to balance it up. And start with the nitrogen. There's 2 on this side. There's only 1 on this side. So let's put a 2. That's going to change nitrogen to 2. It's also going to change my hydrogen to 6, which actually I like 6 much better than 3. Why? Well, look at hydrogen as a diatomic. That means it's a multiple of 2. If it had stayed 3, there's no coefficient I can put in front of a multiplier of 2 to get 3. So I much better like 6. So I can put a 3 here and this changes to 6 and we are balanced. So what we actually have going on is 1 nitrogen diatomic molecule combines with 3 hydrogen diatomic molecules to produce 2 of our ammonias. See what else we've got. I'm gonna do one more together with you and then I'm gonna have you guys do a couple. So KClO3. KClO3 breaks apart into KCl and oxygen. So we've got K, we've got Cl, and we've got oxygen. I start with 1 potassium, I start with 1 chlorine, and I start with 3 oxygens. I end with 1 potassium, 1 chlorine, and 2 oxygens. So right now, you know, potassium and chlorine are balanced. Oxygen is the one that's weird. Again, this is a multiplier of 2. So there's nothing in front of here that I can put to get to 3, right? So what do I need to put in front of here to get this into a multiplier of 2? A 2, that's the lowest thing, right? So if I put a 2 here, I know that's gonna change these and they were balanced and now they're not, that's okay. We'll put the 2 there, that's gonna change this to 6. 6 is much better because now I can put something in front of here. Specifically, I can put a 3, which will bring this to 6. Finish it up by rebalancing my potassium and my chlorine. So we'll put a 2. This becomes 2, and this becomes 2. And now we are balanced. Is this making a little bit of sense? What we're trying to do here? I think the practice is the best thing just to kind of figure out how to like finesse it so that we can do it. So let's practice. So I'm gonna have you guys do a few here. Let me zoom in a little bit. So let's do, let's do 3, 4, 5, 6, and Yeah, 8, 9, I don't know, 10. Yeah, let's do these. 3 through 10. So I will give you all, what are we at? 10, 10:02. I'll give you all about 8 minutes for those. Okay, so if you didn't get to all of them, that's okay. We're going to go through them here. Transfer them over to my whiteboard. So start at the top here. All right. So first, I always like to take inventory. So this one here, I've got sodium, chlorine, and fluorine. I've got 1 sodium to start with. I've got 1 sodium to end with. I have 1 chlorine to start with. I have 2 chlorines to end with. I have 2 fluorines to start with and 1 fluorine to end with. I like that there's like 2 and 1 on both sides. It should be a pretty easy fix. So we can start with chlorine. So I'm going to put a 2 here. That'll balance that out. It'll also change my sodium. That's okay. We can then balance sodium by putting a 2 here. That'll give us a 2 there, and it'll also change my fluorine. Everything's balanced. So you should have a 2 on there and a 2 on there. Next one, the synthesis of water. So I've got hydrogen and oxygen, 2 hydrogens to start with, 2 hydrogens to end with, 2 oxygens to start with, 1 oxygen to end with. So I got to multiply this by 2. That'll change that to 2. It'll also change my hydrogen to 4. That's okay. I can quick fix just by putting a 2 there. We now have 4 and we are balanced. So it's 2 hydrogen diatomics combined with 1 oxygen diatomics to produce 2 waters. This next one here, this is a situation where, do you see how the OH breaks apart? Like it's no longer OH. So you got to take care, like inventory separately. So we don't have, we have PB, we have Cl, and we don't have OH, we have O's and we have H's. So just separate that out. So I have 1 lead to start with. I have 1 lead to end with. I have 1 chlorine to start with. I have 2 chlorines to end with. Oxygens, I have 2 oxygens to start with. And at the end, I only have 1. And hydrogen, I've got 3 hydrogens. So there are 2 here and the third one there. So make sure you add them all up and 2 hydrogens to end with. So I'm definitely going to stay away from hydrogen because it's split up. I'm going to try and balance everything else out and hope that works. So if I've got 2 chlorines on this side, I could balance out my chlorine by putting a 2 here. That gives me 2. That changes my hydrogen to 4 now, and I like 4 much better. 4 is much better because then what can I put in front of this over here, the water? If I put a 2 in front of the water, that changes our hydrogen to 4, and it also changes our oxygen to 2, and now our oxygens are balanced. If you were like, well, I balanced the oxygens first, and then I went and did the hydrogen, that's fine. There's a couple different ways, but your coefficient should be 2 and 2 for this one. This next guy here, sulfate stays intact here, so I can't take inventory of it as a whole. So I've got aluminum, I've got bromine, I've got potassium, and then I've got sulfate. I start with 1 aluminum. Sorry, it's a little smushed here. I end with 2 aluminums. I start with 3 bromines. I end with 1 bromine. I start with 2 potassiums. I end with 1 potassium. And I start with 1 sulfate and I end with 3 sulfates. I like that there's 2s and 3s on both sides. It makes me think that we'll probably get somewhere around 6. For some of these. So aluminum, let's do aluminum. There's 2 on this side, so I need 2 on this side. So I'm going to put a 2 here. That's going to change my aluminum to 2. It'll also change my bromine to 6, which I like, because 2 and 3s multiplied together give us 6s. So we could balance our bromine. If there's 6 on this side, I need 6 on this side. So I'm going to put a 6 there. That'll change bromine to 6. It'll also change potassium to 6. So now I need to get 6 on this side for my potassium. Well, if I put a 3 here, that changes this to 6. It also changes my sulfate to 3, and we're balanced. Again, if you balance sulfates before you balance potassiums or something like that, it will be fine as long as you end up with a coefficient of 2, 3, 6, and then there's an inferred 1 here. This next set of 3, these are all combustion reactions. Okay, you can see there's some sort of hydrocarbon. They're combining with oxygen, and you produce CO2 and H2O. That's what it is. So when you're doing these, always balance carbons first, then balance hydrogens, then deal with oxygen. Okay, so carbon, hydrogen, oxygen. I'm going to first do carbons, 1, 1, then hydrogens. I've got 4, 2, oxygens, 2, and here is 3. So leave oxygen to the end. Carbon is good right now, hydrogen isn't. So if I throw a 2 in front of here, that will balance out my hydrogen and it will give me oxygens of 4. I like that anyway, because then I can put a 2 in front of here and we get 4 and we're balanced. Okay, so let's do this one. This one's a little bit trickier. I've got carbon, hydrogen, oxygen, 3 carbons. I don't know why that's 3. Okay, 1, 8, 2, 2, and 3. So first carbon will balance. There's 3 here, so I need to have 3 here. It changes this to 3. It changes my oxygen to 6, 7. Hydrogens, I've got 8 on this side. So I need 8 on this side. So what can I put in front of here to get 8? If I put 4, that will change this to 8. And it changes my oxygen to, what we've got 6 and 10. Okay, what can I put in front of here to get 10? If I put a 5 there. Whoa, what happened there? This isn't the messy one. I think it's the next one that's the messy one. 5. That will change this to 10. And we're balanced. So 1 is that propane. 1 propane combines with 5 oxygens to produce 3 CO2s and 4 waters. This guy's a little messy, so I'll show you a quick trick for it. Actually, I'm just going to erase this bottom one here. So I have carbons, hydrogens, and oxygen. I have 8 of these and 1 on this side, 18 and 2. 2 oxygens and 3 on this side. So always balance your carbons first. So 8 on this side means I'm going to put an 8 in front of here. That gives me 8 of these. It changes my oxygen to 16, 17. Now I need to change my hydrogen, right? So I've got 18 on this side. So in order to get 18 on the other side, well, what's half of 18? It's 9. So I'm going to put a 9 here. That's going to change hydrogen to 18. That's going to change my oxygen to what? 9 plus 16 plus 9, 25. So this is where you will get a half coefficient. What can I put in front of here to get 25? Well, if I put 25 over 2, that will give me 25, right? 25 divided by 2 times 2, last I checked, that would be 25, right? Anything divided and multiplied cancels out. So this is a correct ratio. What don't we quite like about it? We don't like halves, right? So what do I need to multiply everything in this equation by? If I multiply everything by 2, that will get rid of the 2 here, right? So what is your coefficient on the first guy? It becomes a 2. Let's go away. Put it over here. 2 times. Okay, so this becomes a 2. This becomes just 25. This becomes 16. And that will become 18. 16 and 18. So I just literally multiplied every coefficient by 2. That's the best way to do some of these more complicated combustion reactions, is get your carbons, get your hydrogens, get your oxygen. If the oxygen happens to be over 2, multiply everything by 2. When we go back and check, this is 16 over here. This is 36. Yes, 36. This is 50. This over here is also 16. Hydrogen is 36, and this is also becomes 50. Okay, so you will be balanced. That one's kind of a mess. The last one we had, where are you? There we go. Fe iron 3 chloride. Okay, iron 3 chloride plus sodium hydroxide produces iron hydroxide plus sodium chloride. All right, I've got iron. This one's kind of easy after the last one, chlorine, sodium. And in this case, hydroxide stays intact, so I can take it as 1 unit. I've got 1 iron, 3 chlorines, 1 sodium, 1 hydroxide. I end with 1 iron, 1 chlorine, 1 sodium, and 3 hydroxides. So if I put a 3 here, that will get rid of, that'll change this to 3. It'll change my sodium to 3. Then I can put a 3 here. That'll change this to 3 and this to 3, and we are now balanced. Questions on balancing? What if you're not given it as a skeletal formula? Because that does happen sometimes. Other fun worksheet do I have here? So if you want to do more practice or you want access to that worksheet because you want to redo them, they are in the worksheet section for chemical reactions. I've got another one in here that is word problems. So let's try that out. So we'll go down here. So what if instead of giving you the skeletal formula, it says this, hey, sodium combines with chlorine to produce sodium chloride. Write a balanced equation. Sodium combines with chlorine to produce sodium chloride. So you have to do the first step of writing out that skeletal formula. So let's do that. It's important that you make note of anything that is a diatomic. So for this first one here, sodium is Na. If it gives you the phases, you can write the phases. So I'm going to put a little S here. It doesn't give me the phase, but I know that sodium is a solid. It's a metal. It combines. So anytime you see combines with, that means you're adding. Chlorine is Cl2. Why is it 2? It's a diatomic. If you don't put it as a 2, it will throw your balancing off. This is a gas. To produce sodium chloride, NaCl. I need to balance it with its charges. So first things first, and this is to produce sodium chloride. We'll say that this is solid. So the first thing is to get everything written correctly. So a lot of times when I have these, I will like go ahead and underline, okay, I need sodium, I need chlorine. I'll circle the produce because I know that separates what my reactants are from my products. Find all the things, I'll write them out. And then once I've written them out, then I get to balance. So here we've got NaCl, I've got 1 sodium, end with 1 sodium. I've got 1 chlorine. I end with 2 chlorines, and I end with 1 chlorine. So I'll put a 2 here. That changes both of these to 2. So I need to put a 2 here to balance it out. If you had written it like this, oh, sodium and chlorine, that just means, okay, I've got sodium and chlorine and it produces sodium chloride. You would think you are already balanced, right? But you're missing the diatomic. So always check. Ask yourself when it's in elemental form, is it a diatomic? So that one wasn't too bad. Let's look at the next one because it's a little more cumbersome. When solid copper reacts with aqueous silver nitrate, the products are aqueous copper 2 nitrate and silver metal. Okay, so we've got to do our nomenclature. First thing I'm going to do is just underline some of the stuff. So I need, I have a solid copper reacts with aqueous silver nitrate. I'm going to circle the to produce. You can use whatever. I just like to circle because it kind of keeps it separated, the reactants and the products. You can do it however you want. Aqueous copper 2 nitrate and silver metal. So the first thing I have to do is write those things out. So solid copper, Cu, oh, come on. Let me narrow that anymore. Okay. So copper is Cu. Ask yourself, is copper a diatomic molecule? No, none of the metals are. It says it's solid, so I'm going to add that little S in there. Reacts with aqueous silver nitrate. So silver nitrate, you've got to go silver with a plus charge, nitrate with a minus charge, flip-flop, it's a 1-to-1. So AgNO3, and it says it's aqueous. All right, so I've got to go from this to this. The products are, so now we've got our arrow. I've got aqueous copper 2 nitrate. So what is copper 2 nitrate? That means that it's copper with a 2 plus charge combining with nitrate, which is always a minus charge. We flip-flop. When we flip-flop, we get CuNO3 2 plus silver metal. Ag, and I'm just going to say it's a solid. Oh, they said this was aqueous, right? AQ. So that's the first step, is just getting the right things in the right position. If you've forgotten nomenclature and naming, it makes the rest of this a little bit more challenging. So you might have to refresh. All right. So what do we have? We have copper, we have silver, and we have nitrate. And in this case, nitrate stays intact. So I can take an inventory of it as a whole. 1 copper, 1 silver, 1 nitrate to start with. I ended with 1 copper, 1 silver, and 2 nitrates. So the only thing that isn't balanced is the nitrate. Let's balance the nitrate. Put a 2 in front of this. That changes the nitrate to 2. It also changes the silver to 2. Real quick fix. We just throw 2 in front of that silver and bada bing, bada bang, we are balanced. So I want you to do 3. Solid iron 3 oxide and carbon monoxide gas produce iron metal and carbon dioxide. Write a balanced equation. So I will help you by underlining what we're talking about. We've got a iron 3 oxide, we've got a carbon monoxide. I'll circle the produce. We've got an iron metal, and we've got a carbon dioxide gas. So first thing, write out each of the formulas and then balance from there. I'll give you all about 3 minutes for that. All right, so let's look at 3. So it says the first thing is solid iron 3 oxide. So iron 3 oxide, what is iron 3 oxide? Well, it's iron with a 3+ charge, and it's got oxygen, which is 2-. It's a metal and a non-metal, so we need to flip-flop. So our first formula should be Fe2O3. It says it's solid, so I can add a little S there. Carbon monoxide gas. So carbon monoxide is CO with a little g. Produces iron metal. So it's just saying iron. Is iron a diatomic? No, so I don't need a 2 here, but I'm going to make it a solid because it says it's the metal form. And then carbon dioxide gas. Carbon dioxide is CO2. So the oxygen, that looks a little bit messy. Look more like a G. Okay. So this is the first step. Now we can go ahead and balance. I've got iron, I've got oxygen, and I've got carbon. 2 of these, 1 here, 4 oxygens, 2 oxygens over there, 1 carbon, and 1 carbon. I guess I'll balance the oxygens first here. Well, balance the iron. So I've got 2 there, so I need 2 there. So that changes that to 2. Oxygen, there's 4 there. So I need 2 here, which will change this to 4. Oh, this one's a pain. This one goes around a couple times. So that changes this to 2, which means that I need to then change this to 2. If I change that to 2, it changes this to 2. It then also changes this to, we've got 3, 4, 5. So I got to go around again. Oxygen, so I'm going to try 4, 2, 4. That will change this to 4. It'll change this to 4, 5, 6, 8. Okay, if that's a 4, then I'm going to change this to 4. That will change this to 8, and I'll change that to change my carbon to 4. Okay, yeah, there we go. So sometimes you have to play around, you have to go around a couple times to try and get it to balance, especially when the oxygens are split up like that. Okay, we've got a couple minutes. I want to go over a couple more slides. There is more practice with these if you want, and the answers for these are also there. So you can go ahead and check yourself by working through those. So when looking at an equation, we need to talk about solubility and aqueous solutions. So if something is aqueous, or rather a compound is considered soluble when it dissolves in that particular liquid. A compound is considered insoluble when it doesn't dissolve. And an aqueous solution is a homogeneous mixture where a substance is dissolved within water. When ionic compounds dissolve in water, they usually will dissociate into their component ions. So like if I have NaCl, when that's aqueous, it's not really this as a unit, it's actually sodiums and chlorine, sodium pluses and chlorine minuses floating around. Okay. That's why this becomes what's known as an electrolyte solution when you have dissolved salt in it, because you can run a current through it. So if we had pure water and we had a circuit, we wouldn't have an actual closed circuit with a battery, the light bulb wouldn't work. But if we had added table salt, the dissolved ions create an electrical charge that we can conduct the electricity through. So we call this a strong electrolyte solution. So, you know, when you buy, you know, expensive Gatorade and it's, or expensive water and it's like electrolyte water, it's really just got dissolved salt in it. If you have an aqueous solution with a polyatomic ion, the material will break apart, but the polyatomic ion usually doesn't break apart, okay? It stays as a packet because in this case, like the silver nitrate, the bond between the silver and the nitrate is relatively weak enough for the water to pull apart, but that bond between the nitrogen and the oxygens within each nitrate packet is strong or too strong to be broken apart by the polarity of the water. So it will stay as a packet. Then you have things like AgCl. This doesn't dissolve in water, okay? I take a hunk of silver chloride and I drop it in water, nothing is gonna happen. It's not gonna dissolve. So we would classify that as insoluble in water. Again, a compound is soluble in a particular liquid. If it dissolves in the liquid, it's insoluble if it doesn't. For many ionic compounds, they dissolve in water, but how do you know? Well, there's all these rules. They're called the solubility rules. You do not have to have the solubility rules memorized, but you do need to be able to reference or read these. So these are compounds that are mostly soluble in water. How you would read this chart, for instance, if it has lithium, sodium, potassium, ammonium nitrate, or acetate, these things always are soluble, okay? They just like to dissociate. If it has chlorine in it, you have to ask yourself a second question. So normally chlorine is soluble. But if it happens to be combined with silver, mercury, or lead, it will be insoluble. Okay, so if it has one of these, it's insoluble. If it doesn't have one of these, if it combines with anything else, it's soluble. So that's how you read that. There's another one that says, you know, that you read in the opposite direction. So these are mostly insoluble. Usually if you have OH, it is going to be insoluble, meaning it's not going to break apart. If it happens to be combined with one of these guys, it will be soluble. If it's combined with one of these, it's slightly soluble. If it isn't combined with any of those, it's just classified as insoluble. Again, these solubility charts are not something you have to have memorized. They're in an appendix in your book. You just need to be able to reference them. Here's another way that the solubility charts are written. Okay, great. So in some instances, certain things come together, like let's say we have OH with lead. If you have lead and hydroxide, it is going to be insoluble. So I would put a little S next to it. This means that it's a precipitate or a solid. So sometimes when you mix two things together, a precipitate will form. It's really easy to see it in the equation because it'll have an S. So look at this equation here. This thing is aqueous. It's going to combine with this thing that's aqueous. What happens is the partners flip-flop. So this thing kind of combines with this thing and this thing combines with this thing, right? And what happens is when the lead bumps into the iodine, it forms a solid or a precipitate. What's the other thing? Aqueous. It's really easy to see that this is what we would call a precipitate reaction because it's something aqueous combining with something aqueous, and all of a sudden, pow, we get a solid forming. How this looks, this reaction wouldn't form. This is a non-reaction. We have something aqueous combining with something aqueous, and none of the possible options would form any sort of precipitate, so we would call that no reaction. We'll stop there. We'll get into more into precipitate reactions and how to look at them on Wednesday. So yeah, you guys are good to go. You shouldn't have any homework or labs due this Sunday. You'll have them due at the end of your spring break. So just keep an eye out for that. You could do whatever you want, but I think the last day that they're due is April 4th. So I will see you all on Wednesday. Stay around if you have a question. Otherwise, enjoy the rest of your day. Bye, everyone.